Hello my dear students, and welcome to this video in which I will show you how to model and simulate the quarter core model. First, what is meant by quarter core model? Quarter core model is used to model and simulate the suspension system of a vehicle. It assumes that we have 4 corners of a car and we are modeling only one corner. As you can see in this picture, we have here the chassis with MC. This chassis have a motion of yc of t. The chassis is connected to the wheel via suspension system, and the spring with a stiffness equals to K1, damper with damping coefficient equals to C1. The suspension system has mass ms. We have K2, which is the stiffness of a tire, and C2, which is the damping coefficient of a tire. We will neglect C2 for this example, so please take care of that. The suspension system moves with ys of t, and we have input from root x of t. It may be step input or sine wave input. We can consider the suspension system as two masses blocks, MC and MS. MC is connected to MS via K1, C1, and it moves with yc of t. M suspension moves with ys of t, and the tire stiffness equals to K2, and damping coefficient of tire equals to C2, which in our case equals to 0. So let's see the equation of motion for this system. By balancing the forces on MC, we have MC yc double dot plus C1 yc dot plus K1 yc equals to C1 ys dot plus K1 ys. For the suspension mass, we have ms ys double dot plus C1 ys dot plus K2 plus K1 times ys equals to C1 yc dot plus K1 yc plus K2 times the input x. Arranging this equation will make it easier to model this system on the Simulink. So yc double dot equals to 1 over mc times C1 times ys dot minus yc dot plus K1 times ys minus yc. The second equation, ys double dot equals to 1 over ms times minus C1 times ys dot minus yc dot minus K1 times ys minus yc plus K2 times x minus ys. So, as we have stated in the previous example, we have yc double dot. We will integrate this for the first time to produce yc dot, and we will integrate it again to produce yc, which is the response of the chassis. And also for ys double dot, we will integrate it 2 times to get ys, or the suspension movement. And we will feed back yc dot yc and also ys dot ys in order to complete the model. So let's see this on the Simulink. As you can see, I have created a new model. From the Simulink blocks library, I will add the following blocks. From continuous system, I will add integrator. From sinks, I will add a scoop. From commonly used blocks, I will add gain, and also I will add sum. And from sources, I will add the step input. Let's move this from here. I have created M file. This M file contains all the values of the different variables. So I have MC equals to 60 kilogram, which is quarter of the chassis mass. I have M for suspension equals to 12 kilogram. I have K1 for the suspension system equals to 23 Newton per millimeter, and the damping coefficient of C1 equals to 30 Newton second over millimeter, and the stiffness of the tire K2 equals to 700. So I will run this script, change folder, and if I get back to the workspace, I will find that the different values for our variables. Now back to our model. The first equation we have here, 1 over mc, 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 I'll wire this. This signal here is YC double dot. If I integrated this signal for the first time, I will produce YC dot. I want to copy this block again. So again, if I integrate YC dot, it will produce YC. And now scoop. So this is the first equation. The second equation I have here, 1 over ms, and also I will have two integrators. So I'll copy and drag them and wire this signal here and this one here, and another scoop, wire this here. So this signal here is ys double dot. Integrating the signal will produce ys dot. Integrating again produces ys, and the scoop to look at the graph of ys. Now, in order to complete the model, we need to add summation point. By looking at the equation, we have yc double dot equals to 1 over mc times c1 times ys dot minus yc dot. So this c1 ys dot minus yc dot is repeated in both equations. So I will take a signal from ys dot and subtract it from yc dot signal and multiply them times c1, and I will use this in both equations. So first I will flip this block and I will take the signal. This is yc dot and this is ys dot, and I need to change the sign. Yc dot is in minus, and the output of this signal will be multiplied to a gain block, which is k1. So I will copy this, right click and flip. This is k1, and I will add another sum block. Right click and I will flip. I will change the shape of this block to rectangle. And plus plus. Now OK. I'll expand this. Again, looking at the equation, we have to sum c1 times ys dot minus yc dot plus k1 times ys minus yc. So I need to make k1 times ys minus yc. Again, I will copy this block. I will take the signal of ys and minus here, and the signal of yc, and another gain. Sorry, this one is c1, not k1, but this one is k1. Now, to complete the model, I will wire k1 signal here and c1 signal here. So now I have developed the first equation. In order to build the second equation, I will add another sum block. So I will copy this one. Let's wire this here and wire this one here. We need to subtract signal c1 times ys dot minus yc dot and signal k1 times ys minus yc and add them to this signal k2 times x minus ys. So first I will change the sign of this block to minus minus plus. OK. I will take signal from here and wire it to minus. And from this signal also and to minus. Now I need to make the signal of k2 times x minus ys. So this is the step input. And I will copy this block. This is k2. And I will copy some point. Step input is in the plus, and I will take a signal from ys in minus, and the output signal is multiplied to k2. Then the output of this signal is added to this point. Now we have built a second equation. I will change the step input to, for example, 30, which means a pump of 30 millimeters. And now I can run the model. Double click the scoop to see the response of the chassis. As you can see, after 1 second, we hit a pump of 30. The chassis is up to maybe 42. And because of the damping, the motion is being damped. If I look at the response of the suspension, this is the response of the suspension. We have some oscillation until damped. I can change the value of the damping coefficient, for example, to 20. And I will run the model again. Now let's see the response of the chassis. Again, the motion is being damped. And this is the response of the tire. We have also some oscillation. Let's, for example, try to increase the damping coefficient. Run the model and check the response of the suspension system. Now, as you can see, the oscillation is almost gone. And this is also the response of the chassis. We have here some oscillation. This is all for this video. Thank you guys for watching. In the next video, we are going to look at the same problem, but in this time, instead of modeling it in time domain, we will model it in S domain using transfer functions. So see you there.